Alrighty, folks, we are jumping into module number 6 here, and we're going to talk about a very cool topic, which is concurrency. So sort of continuing on the theme where we were talking about multiple processes, but with another mechanism in the C programming language known as threads, and doing some concurrent programming. So just a few notes before we get started looking at the course website. Of course, you're working hard on your previous assignments and labs, and we'll have another assignment out and lab. And those have actually been pushed a little bit early to your repositories too, so you have those if you want to get started early. For Module 7, there is an announcement on Piazza you can check out, and there is going to be an online exam. So next week of March 4th, you won't have any homework, but just a exam to take. It'll be all multiple choice. And there is a study guide provided of just listing some of the topics that we've talked about to help you, okay? So the videos on Canvas and associated networking material won't be covered in the class. It's just there to supplement your learning if you're interested. And otherwise, we will take this Module 7 to do a little bit of review during the live session, okay? And if you'd like to make up any of your previous assignments, there's a form here you can fill out, so please fill that out and complete your resubmission by March 12th. Okay, so just a few announcements there. Let's go ahead and dive into the module on concurrency. Okay, so I'm going to go to the slides here, and we're going to dive right in. Okay, so module 6 already, if you can believe it. And just a little warm up for us. And this is something, a personal, I guess, something that I like to see in the real world. But when you go to a buffet, you don't want to set up a table like this, right? You want to slide the table out a little bit, and then you can get your food faster, right? You can have 2 lines of people at either ends of the table serving food concurrently, okay? So this is a real picture of some of my friends I took at a buffet that was set up, and eventually I did convince them to slide the table over so we could get served faster. And of course, I was giving a talk on concurrency. So, this is where this comes from. So concurrencies everywhere in our real world. We'll see a few examples of that as we continue. So again, just on the course logistics that I mentioned, you can do git pull from your repo and get A6 and lab 6. And I had a few folks also reaching out that wanted to have a little bit more interaction. So I'm happy to post on Piazza or find some mechanism if folks would like to start working in study groups or form, a weekly meetup with some of your peers. Just let me know if you have ideas for that, or go ahead and create a Piazza post and I can pin it or put a Google form up or whatever for folks who might be interested in that, okay? So I'm happy to help folks out. And again, this is just the write-up on the initiative that I mentioned. So for week 7, again, you'll have an exam, so you get a little bit of a break from homework. The exam itself is going to be 100% multiple choice, and it's really just to give you an opportunity to catch up a little bit as far as the makeup assignment. If to go back and fix something that might be a lot easier for you now that you've learned more C programming and data structures and so on. So you have that opportunity, but also just again to collect your knowledge, sort of reflect on things that you might think you need more practice on, whether they're data structures, pointers, dynamic memory, or those kind of things. So just keep those in mind. And you're not really missing anything out on the networking. Sometimes in this course we get to it, sometimes we don't, but you will have a few supplemental videos available if you go on and decide to take a networking course later. So just some notes on that. Okay, so let's go ahead, and obviously we're recording. Last class, what we worked on was our sort of crash course in computer architecture. Again, talking about that fetch, decode, execute cycle by von Neumann. Then we talked a great bit about the memory hierarchy, about caching, how we introduce the cache to improve our performance, and some examples of the principle of locality, okay? That our hardware makes this assumption that data we use is going to be frequently accessed in time or in space. So that's a hardware assumption that's made so that we can speed up our processors, okay? And then we finally, by the end of the lecture, debunk this myth of how do our CPUs, multi-process or sort of multitask, and it's because they're doing context switches very, very quickly in sort of doing this time sharing mechanism, okay? And then you got to learn about how to create multiple processes in your lab and in your assignment with the fork system call. Okay, so today we're going to talk about concurrency. But first, we need a little bit of wisdom, and this comes from Edsger Dijkstra, famous computer scientist, who says simplicity is a prerequisite for reliability. And today we're going to complicate things just a little bit by making them concurrent, but the same principle applies. In general, it's easier to build, more complex abstractions once you have sort of very concrete fundamentals and building blocks that are easy to use, that we're comfortable with working with. And that's in large part what C is good for. Sort of taking some of these fundamentals and then building up different data structures slowly over time. And then you can add some more fancy stuff like we're going to do with concurrency. Okay, so who is Dijkstra? He is a Dutch system scientist, computer scientist and mathematician. And he made many contributions to algorithms and data structures. And you may have heard of Dijkstra's algorithm. We'll get to see it again later. And he we'll see his other invention, semaphores, today. He's another Turing Award winner. And he has many, many famous quotes. This one I like, that program testing can be used to show the presence of bugs, but never to show their absence, okay? So that's why we always encourage writing as many, unit tests as possible, because the more you test, the more you can try to find your bugs. You might not find all of them, but, you can try to find more. So kind of a word or a thought about testing there. Okay, so talking about concurrency, what we mean here is the fact of two or more events or circumstances happening or existing at the same time. Okay, so that's what concurrency is. In humans, when it comes to concurrent thinking, if you've ever sort of heard that, you should be a good multitasker, humans are actually pretty bad at multitasking for the psychologists who have studied this. Because we tend to think very sequentially, one thing after the other, right? When you're, juggling multiple things at once, whether it's multiple homeworks or jobs or whatever, things get a little bit more stressful and more difficult. So, we're good sequential thinkers. So instead, we want to rely on our computers to do the multitasking. So computers, on the other hand, can do multitasking quite well, right? We showed that last lecture where we had hundreds of processes running at a given time on our machine, right? Even if it's just hundreds of Chrome tabs open. But there is a little bit of a difference here that I want to make sure you understand with these words that sometimes get confused, but in computer science, they really mean two different things. So parallelism versus concurrency. So concurrency means multiple things can happen at once. The order matters, and sometimes tasks have to wait on a shared resource, okay? So things concurrency, they can happen at once. Multiple things can happen at once, but sometimes there's an ordering that needs to take place. Parallelism, on the other hand, perhaps easier to understand, is just saying that everything happens at once, instantaneously, okay? It is in parallel, okay? So here, again, is the difference with concurrency. Okay, a way to visualize this, again, a concurrent event, is two, you have these two sort of lines, so two pairs of people can line up, together. We can have two lines forming at once. But if we have one shared resource here, this coffee machine, only one person can access this shared resource at a given time, okay? So we still have some stuff that's happening, in at once. Two people might walk into a line together at the same time, so that's sort of parallel, but they only get to access this shared resource one at a time. Versus parallel would just be having two coffee machines. So you could always, serve coffee together two at a time here with two different lines. Okay, so all programs that are parallel are concurrent. That's what it means. That's what's being represented here. And this is all the other programs. So here's our sequential, all the programs that we write. A good chunk of them are becoming more concurrent, and then, even a smaller subset of those run in parallel. And in 10 years or so, this space is going to grow. So it's really important that we learn some of these concepts, because concurrency and parallelism is going to become more and more important, right? This is because of Moore's law ending, and now we're getting more CPUs on our machines. So if we have more CPUs, they need to work together concurrently or in parallel. Okay, so 10 years from now, even less, even today, programs are becoming more and more concurrent. Okay, and why do we like this concurrency or parallelism? Well, we actually have another law here by Amdahl. This is by Jean Amdahl, who came up with this law that basically what it says, you don't have to memorize the equation, but it basically says that there's a certain portion or ratio of our program that runs in serial, maybe when you first start up things. But for the portion of the program where you can run things in parallel, that's where you can get your speed up, right? You can imagine throwing infinite processors at a problem that can be solved in parallel and doing something very, very fast. In fact, you're going to get a little bit of exposure to that in your lab today about doing something in parallel and speeding it up. Okay. So another way to understand concurrency, as heard in music, is you have a conductor here conducting an orchestra, and maybe you have the strings playing all at once, so they're concurrently playing, and then meanwhile the woodwinds and the horns and the drums are waiting, but then the conductor here can tell other instruments to play concurrently. So you have this sort of ordering that matters, because that's how you have to make music. Not everybody can just play at once, otherwise then you just get noise. But this ordering actually matters, and sometimes the instruments are playing together, sometimes they're waiting for the other instruments. Okay. Another way to think about concurrency is it's good conversation at a dinner table. Right? People take turns to talk. Maybe these folks are talking to each other here. Maybe some of these folks are listening, versus everybody talking at once, again, it is noise. Or nobody talking at once is probably very uncomfortable. So different ways to think about concurrency there. Okay. And then there's also, remember, concurrency, we have shared resources. So, this guy's reaching for his glass here, but you have to share them, right? So not everybody can get access to these resources at once, right? Everybody has their own plates, so usually only one person gets access to a plate at a time, or maybe you share occasionally, but that's again the idea of concurrency, okay? And oftentimes, you might even think about these people competing for resources too. So this guy's competing for another glass of wine or whatever here. So another thing to think about here, okay? So with concurrency, which is what we're focusing on today, like parallelism, it's used though because it's necessary for a system to function, right? Think about your dinner table or your orchestra. It's necessary to have some sort of ordering where only some instruments play at a given time in order for things to function, right? Just like at the dinner table. Not everybody can grab the same thing at once, okay? So there's other familiar examples of this, right? Subway transit systems, you can have multiple trains running, but not all of them can be at the station at once. Cars have to stop at traffic lights while other cars can proceed, and so on, okay? In computer science, just to put this in the context, right? Even your memory allocator, right? It has to pause for a moment when you're allocating memory because, well, if two processes are asking the operating system for memory, they're doing malloc at the exact same time. What happens if they both granted the same piece of memory to each process? Well, that would be a problem. We're gonna learn. So even with a memory allocator, as long as the operating system isn't handing the same memory to each process, you're fine. Okay. So there is some concurrency here. Okay. Another thing with concurrency, these are examples largely motivated by increasing performance. So again, the potential for more tasks to happen at once means you can do more things in parallel, thus speeding up your program. And that's exactly what Amdahl's law is. Okay. So this all sounds great. Let's write concurrent programs, but this does come with some caveats, however. Okay. So I'm going to give you the three major problems with concurrency. And the first one is what's called a data race. Okay. So this is when two or more processes, so again, we can think of this in computer science, our processes contend for one shared resource. Okay. So in this example here, there's one parking spot for two cars that they want to acquire, right? So if they acquire it at the same time, you get a little car accident here. Okay, so that's a problem. That they both raced for this parking spot, so you can remember that data race there. And we had an accident here. Okay. And the data race itself isn't always obvious, right? This one's obvious. These cars shouldn't be doing this. They could probably see each other when they were coming into this parking spot, right? That one was parked in here, but they tried to acquire the same resource, and nobody won here. But again, these aren't always as obvious, and you can think about this example if you have roommates or partners or whatever. And imagine you're checking your fridge and find there's no milk in it. Okay, so you open up your fridge, there's no milk, and then you decide you're going to run to the store. Okay. Then a moment later, your roommate checks the fridge and finds out that it's empty. And they also say, hey, there's no milk here. I'm going to go ahead and run to the store and get some milk. And then roommate number 3 comes in and notices the same thing. They say, hey, there's no milk, in the fridge, so I'm going to run to the store. I'm going to go get some milk. So what happens then is, all 3 roommates come back and they saw the state of this fridge. It was empty, but then they each add in their, gallon of milk here. And then you have 3 times as much milk as you need, and it's probably going to spoil, right? When everybody, finds out that, there was, some misinformation here. We had this shared resource, and every time we solved, it was in a sort of different state, okay? And my question is, this is going to be something that I'll ask you, is, how could we have prevented this from happening, this issue with the milk, okay? And I'll ask you again during the live session, but go ahead and take a moment to think about that. How would you have prevented this from happening? So you don't get 3 times as much milk, right? You've wasted 3 times as much money. If you can't drink this much milk, you're going to have to throw it out. So how would you prevent this? Okay, so data race is one of the concurrency caveats that makes it not always so great. And the second problem is you can run into is called a deadlock. Okay, so that's exactly what it sounds like, but it's a gridlock and a traffic jam here, where here's our shared resource in the middle. A bunch of cars are trying to drive into the intersection and they get stuck, right? This is the shared resource, the intersection. Normally we take turns, but this car here happens to be blocked by a bus, but the bus can't move because it's blocked by this vehicle, but this vehicle can't move because it's blocked by this one, and so on. So we are in what's called a deadlock. Because one of these cars needs to acquire part of this resource so that it can make progress forward, okay? That is the issue here, okay? And then finally, the third caveat, this one's often less obvious, but it's called starvation. Okay, so you can imagine this as a constant stream of cars going by. These green cars are driving through the intersection. And, progress is still being made by these cars. They're still getting to their destinations, but these yellow cars have to wait. They're both trying to make, left turns here. And because the left cars can never acquire this resource, this intersection, for themselves so they can drive through and make progress, we say that they're starved. They're resource starved of a shared resource. Okay, so again, they have to wait and wait and wait, potentially forever. But it looks like, if you looked over this in the real world, you'd say, hey, there's nothing wrong. The green cars are still zooming by, but these yellow cars aren't able to make any progress. Okay. So, we have those are the sort of real world analogies for the programming issues that can happen when you have multiple processes, right? Just pretend each of these cars are a process that can never make progress forward, while some of your processes can, okay? Same issue with deadlock. When your system locks up and you can't do anything, chances are there may have been a deadlock, okay? And then a data race is when something weird happens in your program like this. It wasn't supposed to happen. The rules were sort of broken, but, the situation did happen. Okay. So just to summarize these 3 caveats, a data race is when the outcome depends on the arbitrary scheduling decision elsewhere in the system. Okay, so that data race, for example, with the milk problem, if your 2 roommates never checked the fridge, or checked it after you had come back with your gallon of milk, right? They wouldn't have gone out to the store to get milk. So that's what we mean by data race. Okay, and sometimes this happens also in real life. If you've traveled on an airplane and been the last person on the plane where it's been double booked, who gets the last seat on the airplane? It's sort of just up to some arbitrary scheduling, who bought the ticket first. Or whatever other criteria it's decided upon. Okay, Deadlock, the second caveat, is the improper resource allocation, again, preventing forward progress. So this is the traffic gridlock. Or if you've ever shown up to an intersection and all the lights stay red, okay? And starvation is just an issue of fairness. That is, there's sort of external events happening or something that prevents, some other subtask, our yellow cars from making forward progress. So example of this, starvation could literally be, you're standing in the grocery line and somebody keeps cutting in front of you, right? You're sort of resource starved. Someone's breaking the rules. So they're the external event and preventing you from making progress forward. Okay, but regardless of these issues, these are three well-known issues, the three well-known issues. Concurrent programming is still important and necessary, right? Because we need our orchestras, need concurrency to function, our dinner tables, and so on. Okay, same thing with our programs. We need our systems to be able to multitask. Okay, and there's a few approaches to achieve concurrency. And in fact, we've already looked at one type, which is sort of this process-based, where we have the fork command. Okay, and that was a way to get multiple processes running. Sometimes in parallel, right, where we saw how that worked, where each process made a complete duplicate of itself and then began executing. Event-based is sort of another paradigm we won't look at too much in this class, but again, you sort of have concurrency based off of events that happen. And an example of this is when you're in an application like this, in a PowerPoint presentation, and then you click, something happens, okay? And then, concurrently based off of where you pressed or if you clicked a button or hit a menu, some event starts concurrently, okay? Menu pops up, a new open file dialog or whatever. And then thread-based concurrency, this is what we're going to focus on. This is a new term for us, thread. But this is the idea that our operating system is going to manage a bunch of these things called threads. And they're all going to exist within the same process. Okay, that's what it means by same address space here. And you'll be able to get some multitasking or concurrent behavior through this tool called a thread that we're going to learn about today. Okay, so you can think of threads as a lightweight process. Okay, that's exactly what a thread is, a lightweight process. So it's sort of like a process, but we don't need to duplicate the whole thing. Okay, that's what we're going to find out here. Okay, and in fact, a single process, just a program that you're running, can have multiple threads. Okay, so again, this thread is going to sort of be this separate flow or the separate thing that's executing. Okay. And what's different about threads versus processes is that a thread shares the same code, it shares the same data, and it shares the same context. Okay, so we don't have to do this expensive context switch because the thread is happening within the same process. Okay, so for example, threads have their own control flow, so they can do different things, and they're going to have its own stack, but they'll share all of the other global data, all the other data that you've initialized. So we've got this thread 1 and thread 2 here. They each have their own stack. They might have their own registers and stuff, but they share all the rest of the program code, all the global variables, everything else, all the memory that you've mallocked and so on. Okay, so this is a way to think about threads just at a high level versus processes. Processes on the right here, right? We had this sort of parent-child relationship with different events, different processes being spawned off as children and then executing. A thread, on the other hand, sort of like what we call a pool or pool of peers that are all executing their own command flow, right? These are sort of like their own functions doing some work, but they share all the code, all the data, everything else, okay? And can make use of that, okay? Okay, so here's another way to think of things too. Because we saw this diagram last time when we were talking about concurrent processes and having multiple processes run on a single core and sort of doing this time sharing that was happening, right? This sort of context switch. But with a concurrent processor, we instead have threads here that can each execute on each of our cores, okay? If we have multiple cores. Otherwise, a thread's still doing the same sort of time sharing idea that processes did, okay, from this previous slide. Okay, so threads versus processes. We've learned about processes, but threads are a lightweight process. And the similarities are each have its own sort of logical control flow, meaning just a chunk of code that it's executing. Each can run concurrently or possibly on different cores if you have a machine with 4 CPUs on it or 8 or whatever. And each is sort of context switched, but the thread is a lot more lightweight. It's got less, because it's sharing more information, it doesn't need to, when a context switch, change as much data. Okay, the differences are that threads share all the code and the data, except for the local stack. We'll see what that means when we actually launch a thread. And processes typically don't share anything. They get copies. And then threads are usually, because they're lightweight processes, they're less expensive in terms of the sort of compute power that you need to execute a thread. Okay, so roughly speaking, there are some estimates here that threads are about half as expensive. Okay, this is sort of the number of cycles needed to create and reclaim a thread. Okay, so in order to use threads, we've talked a lot about them. We'll see some examples in a moment. We're going to use in C what's known as the pthreads library. Okay, it stands for POSIX. That's how we pronounce that, POSIX threads. And these are the sort of functions that C gives us, the C language or the C library gives us to create programs that can do things concurrently. Okay, so we're going to have some functions like how to create a thread, joining a thread, which we'll see what that is, but that's essentially a wait in a process. And then we can do other things like get the thread ID, we can terminate our thread, and then we can have some other ways to sort of synchronize our threads so that they can work together. Okay, so we'll talk about that. Okay, so let's look at an example. I'll type one out in a moment, but here's a pthread example, and let me go ahead and launch this here. So I'm going to go ahead and just type it out so you can see again as we build this up. So let's go into the C directory here, and I'll just create thread1.c in my Vim editor. And let me split the window here just so you can see it as we go. So thread1. Okay, so what we're going to do is include our normal libraries, the standard input output, the standard lib for any memory allocation stuff that you might do later, and then a new library called pthread.h. Okay, and this is what's going to give us access to our new thread. Okay, now I'm going to create our main function because that's what we need, and then let's create our first thread. Okay, so I'm going to do this sort of similar to the process, create a pthread, and then I'm just going to start its ID, so the thread ID here. And then I'm going to create a thread. So pthread underscore create. And as parameters, it takes the thread ID. And this is going to then store that value in this variable. The next value here, well, if I can't remember, let's do pthread create here. The second value here is different attributes that you can set for the thread. So these could be things like priority. So if you create a bunch of threads, which one gets to execute first, and so on. So we don't need to worry about that right now. So we'll just put in null here. And then the third argument is the function that you're going to execute. Here, I'll just write this one as my thread, and then any arguments to that function. Okay, so what does that mean here? Well, we need some function here, and I'm going to call it my thread. And this is the function that's going to execute as soon as I call pthread create. Okay, so let's just have it printf, hello from thread. Okay, and then it'll just return null. It needs to return a null value here, just some value here. Okay, and that's it. We've launched our thread here, but we need to do one more thing, one more task here. Which is this function pthread join. Okay, and it's named a little bit weird, but what it is we are going to join this thread, TID that we're storing here, with our main thread of execution. Okay, So that means while this program is running, whenever we start a program, we have a main sort of thread of execution. That's the main function that's executing one line at a time. But as soon as we create this other thread, we have a separate execution that's happening concurrently, right? It's this piece of code here, okay? But we're saying, hey, main thread, this main thread of execution needs to wait until this thread ID finishes its work, and then it can proceed forward, okay? So I'll show you a visual of that in a moment, but let's go ahead and compile this and make sure it runs. I'm going to run Clang. I'm going to try to compile this like we normally do. Here, I'll use GCC. It doesn't really matter. But it's going to give us an error message here. It says undefined reference to pthread create, undefined reference to pthread join. Okay, so this is something new that we might have run into because we've included the header, and we know that we're not getting syntax errors, so these must be valid functions. But what we've actually forgotten to do is include the pthread library. So we have to actually link it in here. So I'm going to link in the pthread library here. Okay, so lowercase l here, no spaces, it's just a -l, and then the name of the library we need to link in. And if I hit enter for that, then we should be good to go here. Okay, and oops, let me make sure I save this, and I'll run it with Clang here. I think this will do the trick. Yes, yep. I think GCC, so Clang here is fine here. GCC is a little bit more picky if you're using GCC. It wants you to add the libraries at the end. So you do lpthread here, and then it's fine. So either way, with Clang or GCC, we have thread here. Okay, so let's actually execute this, and we get hello from thread here. Okay, so this program just launches in a separate thread of execution, this function here, and just starts executing one line at a time. Okay, until we join with our main thread. Okay. So again, just to recap, the thread is launched with the pthread create. It's launching this thread function here with, well, there's no arguments here in our actual thread, so we just pass in null and no attributes as well. And then pthread join, again, is the equivalent of wait for processes. It's saying, hey, wherever this was launched from, wait in this main thread until the thread with this ID finishes executing, okay? Okay, so then you get hello from thread. So here's the visual again of what's happening with the different threads. We have our main thread of execution here just when we start our program. And then we begin executing, we create a variable, and then we call this pthread create function. Okay, and then as soon as we do that, this thread executes, this new thread here that we're creating executes from a new thread of execution here. Okay, so it sort of goes off here. It's a peer thread is the way to think. It's a peer to this program, or just thread one if you want to think about it that way. Okay, so then both of these programs are now executing concurrently at the same time, or excuse me, both of these threads are executing concurrently. Okay, so the main thread happens to execute the next line, which just says, okay, pthread wait. Okay, so it just says, well, now I just get to pause, or excuse me, pthread join. Okay, so it's just going to wait here for this thread to start executing, and eventually when it returns, that means it has terminated. Okay, and then when it's terminated, this main thread sort of behind the scenes gets a little signal that says, okay, this thread's finished its job, so we can return to execute and then execute our next line here. Okay, so that's what's going on with our thread example here. So if you take a moment to pause and write that example out, you'll create your first threaded program. And again, make sure you link in your library. If you do it with Clang, you can put the library there. If you do it with GCC, just remember to link it in at the end. Okay, let's look at some more examples as we continue on. This is going to be thread 2 and thread 3 example. Okay, so you say, Mike, that was interesting to, launch one thread, but why, you don't really need threading for that. So let's go ahead and launch 10 threads in an array here, okay? So let me go ahead and I'll follow along with this example. Again, just so you can see me build it up, I'm going to copy this file here to thread 2. so we can have it also ready to go. And this thread, let me actually give the arguments here. We can have a variable number of arguments here that we pass into our function. And I'm going to modify it a little bit so it just prints out the thread name that is coming. Okay, so pthread self is the function to do that. Okay, I'll make this a little bit smaller just so you can see it all on the same screen. Okay, and this time, let's create an array of these thread IDs. I'm just going to create 10 here. And we'll do this in a loop here. Okay, so for int I equals 0, I less than 10, let's just create the 10 threads. Okay. Now this time, though, we are storing the thread IDs in an array. So, okay, we have the ith thread that we're creating. Okay. And then we want to also join those one at a time with our program here. Okay, so now I'm just going to join each of the thread IDs here. Okay. And then I don't need this here, but I can just say maybe a printf message that says main thread is now executing again. Okay. Just so you can see that we should see all 10 of these threads start executing concurrently and doing work because they're just being launched, 0 through 9 here, each of these threads. And then they're launched, they do their work. And then they also, once all the threads have been launched, they join with the main thread. We send this signal to them that says, hey, make sure that the main thread, which is this guy where we started, stops executing until all 10 of us are done executing, okay? So let's go ahead and try to compile this one here. Let's see if we made any mistakes. Oops, looks like it didn't like that, so I'll take a minute and fix that. Just need to get rid of the ampersand here. Right, and I think that'll do the trick here, and looks like it's good to go. So let's go ahead and run thread here. And you'll see we get hello from, thread with a bunch of different IDs here. Okay, so again, I'll just execute this and you can see all the different thread IDs here. And then the main thread is now executing once again here. Okay, so, these are just the integers here. I was just checking to make sure that we have the right value here. So let me actually go to the man page for pthread self. And this just returns back the thread ID here, okay? And I believe this is just a long integer here, okay? So that's why we have %d. All right, so let's again just recap what's going on here. We're launching 10 threads, one after the other in a loop here. Each thread is executing here. And again, we're printing the ID just so that you can see that, again, these are different threads that are executing here. Okay, so if I go ahead and execute this once more, you can see again that all of these are different threads. So they're all theoretically capable of doing different work, which was printing off this hello message here. Okay. And then we joined all of our threads with the main thread. Again, this is important that we do it for all of them because this makes sure that all 10 of these threads get a chance to execute before the main program eventually prints off a message and then returns and terminates the program. Okay, because once the main thread terminates, everything has completed here. So with threads, we don't have to worry about zombie or defunct processes or anything like that. But we do often want to make sure that all of our threads do get a chance to execute before we return from our main thread. Okay, so here's a new program. Let's actually start doing some interesting work, or rather, do something that involves, a bunch of programs working together. Okay, so I'm going to copy thread 2 into thread 3, and let's go ahead and modify this program again. Here. Okay, so we're going to have a thread function here that we want to execute, and we're going to keep this same structure with 10. I'm just going to crank this up a little bit. Let's define the number of threads as, 1,000. Okay, then I can just pass that on here, and here as well, number of threads. And now I'll make sure that everything's consistent. Okay, so then we can just run some little experiments with 100 threads or 1,000 or even 10,000 is fine. Let's go ahead and do that. But the work I want to do is, sort of a very simple example. And let's just create a counter here. And I want each of the threads that's executed to increment this counter. Okay. So, theoretically, I should be able to add numbers if I have 10,000 threads, 10,000 times faster. Okay, so let's try to recompile this here. We're working with thread 3, and it compiles. Let's see what the result is. Oh, well, I got to print off what the counter is here. So the main thread's executing. Let's just print off the counter variable. Counters in global variable. So we have a value here, and it's just a integer, so %d there, and the counter. Okay. So I run this, and it looks like I got an error here, 9,983. Okay. So that's not right? If we have 10,000 threads, we should be getting, counter that increments from 0. We should be getting what? 9,999. We get 99983. Oh, this time, we got a different result, 9978. Was our program terminating early? No, it shouldn't be because we're joining. So let me run this a couple more times, and I keep getting a different result here. So this can be really bad because we don't have a program. We thought we were using threads and adding up this result really, really fast. But we're getting a different value here, which is troublesome to me because, computers are supposed to work. They're supposed to be good at adding things. So what's the problem here, with our 10,000 threads? Well, counter is a shared resource between these threads, right? They're all accessing this global. And remember, threads are able to share the same memory. So we know that they all have access to this counter here. But as you saw when I ran this program, I kept getting different values, okay, for the addition. So what's wrong with this program? Well, let's try to investigate again by a real-world example. And the sort of prelude to this, as you can remember, are 3 different caveats with threads that can cause problems, okay, that we opened with. And now you get to see what it is and how we're going to fix it. Okay, so let's go ahead and take our look here with bank transactions. Okay, so here's the idea. If I have a series of bank transactions and I start off with, $25 in my checkings account, and I deposit 50, I should have 75 because I've just added $50 to my bank account, and then I can withdraw 50, and now I have 25. My final bank statement at this point is $25, right? Because I've added 50 from my initial 25, and then I took away the $50 that I had in my bank account, okay? So there's some variable, called checkings in our bank account that monitors our balance, okay? Now here's sort of a serial, so that's a sort of sequential or serial set of transactions that took place. But remember, we're working concurrent world, so here's what can happen with a concurrent bank transaction, right? So we have a lot of devices, maybe we do something at the same time. So this time, assume that I have, again, $25 in my checkings account. And then I'm able to, on a phone and a computer, I deposit, $50 on one device, and then I withdraw 50 at the same time, concurrently, okay? My final balance should still be $25, right? Because I've essentially deposited 50 and then just taken back 50, really, really quick. Now the key here, though, is that, again, there's a shared variable called checkings in each thread that monitors our balance, okay? So I'll just highlight that again to say, there's a shared variable, checkings, in each thread that monitors our balance. So anytime we're working with concurrency and we have something that's shared, we have to be careful, okay? So that's what was happening with the counter problem, okay? Because here's what can happen. So here's sort of time as it goes down. And here's our concurrent bank, with our initial shared variable checkings, and we're going to launch 2 threads to do each of the operations, right? Where we have to do sort of the withdrawal process and the deposit process. So thread Y is going to do that on this side, thread Z on the other side, okay? So they start executing, and each of these threads, immediately says, okay, checkings is 25. And then I'm going to do the withdrawal and the deposit action, okay? And then it just happens that thread Y updates checkings next, okay? It just happens in time. That's the next thing that happened. The processor gave just enough time for this to happen. And then thread Z updates its value, okay? So the checkings is 75, okay? But we have conflicting information at this point, okay? Because on this thread, the checkings is 25, and it just happened these instructions sort of interleaved with each other, such that while this was updating the value from 25 and subtracting 50 and just starting to update to 25, then this operation happened where we're depositing and said, okay, we're going to do the deposit, but we're adding to 25. So I have conflicting information. The last value that is in memory is 75, so we report out that I have $75. That's actually great for me. I sort of made money during this transaction, but we know this is incorrect. Okay, and if the operations had swapped, right, it just happened in time that this thread Y happened to have the checkings value updated at the very last moment, then you end with minus 25 in your checkings account. Okay, and that's also a problem because now we're out of money, but we've lost our $50 that we've deposited and withdrawn, right? This should still be just 25. Okay, but then we can also have this scenario too, where thread Y just happens to, maybe we're on just a single core machine and thread Y happens to execute really fast in time. So we get the value when we withdraw 50, we have a minus 25 balance. So checkings is minus 25. Then by the time thread Z starts executing, well, it's going to execute and read that our balance is minus 25. So that's the value we work with, and we deposit, and we get sort of more of a sequential, we just happen to get more of a sequential series of operations here, and then we check out fine here. Okay, so the problem is, in really, only one of these scenarios, we got the right value for checkings, okay? And we have witness, this is exactly what a data race is. We have multiple threads on a shared resource, and depending on the arbitrary order of the events, we get a different result here, okay? So checkings ends up being 25. And this is a very common concurrency problem, okay? So what we really need to do is synchronize these operations, right? We need to enforce some sort of ordering so that checkings, we launch a thread Y and it does some work where we do the withdrawal, and then, thread Z gets executed and it just does the work, okay? So then if we do this, we're always going to get the right answer. Okay, but this is basically just our serial execution. Okay, so we've lost our sort of threading mechanism. But anyway, the way that we can do this, or one way we can do this, and that is to enable our systems to be in a sort of consistent state, is to figure out how to make this portion of the code where we're updating counter act sequentially. Okay, and then the same thing with our bank. We need to make sure that when we're reading this checkings value and doing the withdrawal, that these operations happen sequentially. Okay, because some parts of our program might just have to be sequential. Okay. Okay, so here's how we share data. Okay, and this is a good point because we're about 50 minutes in almost. So if you need to take a break and stretch your legs, please feel free to do so, and then we'll resume and talk about sharing data. All right, so if you've taken a moment to pause and rejoin for sharing data, again, we have to remember what information is shared in a threaded program. In this case, global variables are shared. So that's the example, again, that we just saw with counter, okay? So that's where we have to be careful. Now some compilers are smart enough and can figure out what information is actually shared based off of, if you have different threads that reference different values, but otherwise, we have to be careful with global variables because we know that those are shared amongst every sort of thread. Okay. So again, conceptually, remember that threads run within the context of a single process. So each thread has its own separate thread context, meaning it has its own ID, has its own stack. And again, what I mean by stack is any of these variables. If I create a new variable here in this thread, new variable, each thread will have its own copy of this new variable because that's local. So that's what I mean by the local stack. It also has its own sort of program counter. So each of these threads are executing, each of these lines one at a time, its own registers and so on. Okay, but otherwise it's still sharing all the globals, all the other data, and everything else. Okay. Now this isn't strictly enforced that information can't be shared. So we still have to be, again, a little bit careful because we can pass pointers around in threads. But for the most part, you can think about threads as having only a view of their own local data or otherwise of global data. Okay, and we'll talk about this in a moment of how we have to be a little bit careful with this. Okay. Okay, so again, just defining a few terms here, because again, they become even more important. We've talked about local variables and things on the stack, but just to define them, global variables, again, any variable declared outside of a function, and you only have one global variable ever. So in your memory, there's only one instance of any global variable. Local variables is a variable declared inside a function without the static keyword. So static is something that you can add to your variables. So if I created a new variable here, this is local. If I write the keyword static, this is a static variable. It's not local. It's actually shared amongst anything that executes this function. Okay, which is our third case here. Local static variable. It's a variable declared inside a function with that static attribute. And then that is essentially a global variable itself, but it can only be accessed within a function. Okay, so let me again define some of these. So to map these different variables in memory here. Okay, so here's an example of a global variable. Here's some local variables. Here's another local variable that's just local to this thread again. And here's a variable that's it's marked as static, so it's shared in anything that executes this function thread, whether it's another thread or the next time a single threaded program updated one of these variables, then it would still be updated sort of this value here just as a global. Okay, let's play a little game here, and we'll do this during the live session where I want to know which information I can reference from my threads. So I've got 3 threads. I've got my main thread, and then I'm going to create 2 peer threads, peer thread 0 and peer thread 1. That's what this loop is doing here. And I want to know if from my main thread, can I access this variable pointer, or from peer thread 0 or peer thread 1, can I access pointer? Okay, so I'll give you a moment to pause and actually run through this exercise, and then I will talk through the examples. Okay, so if you've taken a moment to walk through these examples, well, pointer is a global variable, so that means we can definitely access it from our main thread. But remember, our peer threads also get copies of everything that's global. So pointer, we can access everywhere, okay, whether it's in our thread function from one of these threads that we create or just in our main thread. Okay, how about the count variable here? So count is a static int here. Where can we access it? Well, you can pause the video and think about it. And moving forward, so here it is. Well, the main thread doesn't know anything about it, but in each of our peer threads, we can access static function, or static variables, excuse me. Because static variables, again, are all threads share this static value, whatever it is. Okay, so however we update it. Okay, what about the value I here? So I have this long I here, and I have the .m just to indicate that's part of the main thread. Okay. Yes, so it's local to main, but our peer threads have no notion of what I is. Okay. Messages, how about this one? This one you have to be a little bit careful with, because here's messages, so it's declared in main here. But then I'm also going to use this pointer to access and point it to the memory where messages is. Okay, so the answer for this one is yes for all three. And it's yes because, well, message is local to main, so we can see it there. But it can also be referenced by peer thread 0 and peer thread 1 because we have a pointer that happens to be global, so that's accessible to everything, that points to the actual memory where messages is. Okay, so that's one way our threads can sort of share locally allocated variables. Okay, and now these ones here, my ID. So here, where are they accessible? Well, my ID for peer thread 0, when it executes, it gets its own local copy here. So it's just referenced by peer thread 0, none of the other ones. And my ID in peer thread 1 here, sort of the opposite, just in the peer thread reference here. Okay. All right, so that's a little bit of the analysis. So just understanding what gets referenced from what from within a thread. Okay. So super important to keep track of what's available. Those pointer ones a little bit tricky. You have to be, again, careful with pointers. But then you know which information is being shared and where you can have potential issues like data races. Okay. So again, it's useful to use these shared variables for moving around data, but again, we have to be careful to avoid data races. Okay, so how do we fix it? We need some sort of mechanism to protect our shared resources, right? Just like you would use a lock to protect something that's important. We actually use the same thing in programming, which is a lock structure around shared variables that only allow one thread at a time to access that variable, okay? So the idea here is, in our bank example, we would just put a lock around any shared variable. Okay, so any function that we have related to our bank, we could just add a bunch of locks, okay, in each of our functions or within the curly braces. That would be something that we could do. But again, if we put locks everywhere, we have to be a little bit careful because then we're sort of making our program run sequentially. So we're only putting locks around the shared data, okay? Okay, so let's finally try to fix this example, thread4.c, using locks now that we have some additional help, okay? So I'll actually code this example. Let's go ahead and fix it. And save this here, make a copy. And this is a quick way just to give some more files to play with here. Oops, copy thread 3 to thread 4. And let's open up our thread 4 program and fix this. So we know there's a bug here. And what we're going to add, or what's new, is we're going to have a global lock here. So that's what I've created at the top here. So I'm going to add it here. Pthread, and it's called mutex, which means it gives you mutually exclusive, mutually exclusive access to a piece of code. Okay, so I'm just going to call this mutex1, and we initialize it with a special definition here, initializer. Make sure I spell it right. Okay, so that initializes our lock. Okay, we don't set it to null or anything, but we use this. And then we just simply use the lock to wrap. So we have pthread mutex, and then we lock. Which lock are we locking? Well, mutex1. We pass in the ampersand because it needs to know the actual address of this lock, where this guy lives here. Okay, I like to indent here too. So we're going to put a lock there around it. And then when I'm done with the lock, when I'm done doing my work, accessing that variable, then I unlock. Okay, and the same idea here, mutex1. Okay. And that's it with the locks here. So let me try to run this, and if we run it properly, we should get the correct result every single time. And oops, I ran thread 3, so that was the old. Here's the fix. Let's go ahead and run it, and 10,000. Okay, and it should do 10,000 every time. I'm willing to bet on it. We want to run this as many times as we can. Sometimes these errors aren't always apparent, so you do have to run a lot of times to see if you get concurrency errors like data races. But we can be pretty confident this is going to work, okay? because we have put a lock around our shared resource. Okay, so again, here we created the, or initialized the lock here. This is like a key that we have. And then we use that key to lock and unlock when we are done accessing our shared resource. So any other thread that tries to access this resource has to wait. Okay, and again, this works for us. Okay, now the example is truly fixed. Okay, and here's just sort of a joke that, you know, if you have a big bank account, you might have a more serious problem keeping track of your money. So synchronization matters more and more as you work with more data. Okay. Okay, so again, the idea is you're going to lock functions with shared variables. Okay, so when we're working with our bank account example or whatever software we're writing, we always get the same value back instead of 3 different values, right? Which we saw when we did not synchronize or lock our shared data. Okay, so again, and this can be easy, right? You can just put locks around everything. Just put a lock around all of your code. But again, your performance, if you do that, you're just executing sequential code. So you do have to think about this and actually not just use locks everywhere, but only on pieces where there's shared data, things that you care about that the order is correct. Okay. Okay. So, you know, how do we sort of, you know, how does this locking mechanism work? You know, how does this, you know, truly do its job? How do we know it's locking or unlocking? Well, there's actually if you want to read the paper from our author, Dijkstra, he's actually got a nice, the original write-up. You can kind of see the, I think this has been retyped for us, but you can actually read what the mechanism is. It's about 6 pages. It's not required for you to read it, but you can see sort of how they define the algorithm here. And he actually gives another name for this mutex, and he calls it a semaphore. But again, the idea is that you have basically an integer here that can increment or decrement. And based off of that value, that means you are locking or unlocking, okay, the piece of code. Okay, so let's talk about that primitive semaphores. We've just seen one, a very specific instance of this concept of a semaphore, and it's something known as a mutex, okay, that we've seen, or the other name is a binary semaphore. So it's just a lock that can be a value of either 0 or 1, okay, for locked or unlocked, okay. And, you know, mutexes are pretty easy to use, and we can see the actual code that we have here is just, you know, mutex lock, mutex unlock. Now there is a more general version, just called a semaphore, that you can use. I'll show you at the end. It's recommended to just use those if that's all you need. They're simple to use, sort of easy to read, right? There's 3 lines of code we added. Okay. The general purpose semaphore, as we sort of define it, is just a non-negative global integer synchronization variable. That's sort of the long way to say it, but all it is really just a global integer that counts up or down to tell you how many threads are accessing a resource or how many are not, okay? Now, Dijkstra, because he was Dutch, he defined these with the Dutch words for P and V, which I think I might have put in here, but if anybody speaks Dutch, they can remind me what stop and start sort of mean. But you can sort of think of these as sort of wait or acquire or lock operations. Okay, that's what we did. So lock means you get access. Okay, and that's what we did here. So we locked first. Okay, and sometimes you'll see different names for this, like wait or acquire for your resource. And then all that happens is your semaphore S here, if it's some non-zero value, then it just increments by 1 and it returns immediately. So the general purpose semaphore means if you're trying to acquire a resource, you know, and maybe you want 10 threads at once to access, it'll just decrement until it's a non-zero, or as long as it's a non-zero value, it'll just keep decrementing, okay? The equivalent of this is if you're going inside a restaurant and you have somebody, a hostess or a host at the door, and they tell you, you know, yes, you can come in, or no, you can't because we're at capacity, right? They are essentially a semaphore that's doing this counting, right? And they're decrementing by 1 every time somebody leaves. because that means there's one more spot open. Okay, and then the opposite is to unlock. Okay, so that's the idea. Here is a super video somebody did in PowerPoint. This person to describe how semaphores work. I'll just play it in super fast speed. You can watch this on your own. It'll make very clear how this works. It's a little bit silly here. There's a coffee shop, and then I guess the people multiply, which isn't really part of the deal here, but you get the idea that the restaurant's full, so we have to wait until somebody finishes eating, and then this police officer at the coffee shop, I guess, decides that he's going to send a signal and say, yes, somebody else can come in now. Everybody else has to wait, okay? So this is more the general purpose semaphore, okay? And this is all the real implementation is. There's just a loop here that sort of says, hey, if there's if somebody can come in, so this is wait, or your sort of unlock operation, allow somebody to come in. Signal is sort of the locking operation that increments this value. Okay. So here's some of the ideas here. Okay, so and the other question, here's the Dutch for test and increment. So that's why it's P and V. But the idea is, and this is something that I often get a question for, that's why there's a slide here, but how do we know that when we're locking this mutex and not, and also unlocking here, this mutex, that, two threads don't try to do this operation at the same time, right? The actual lock and unlock. Well, this is guaranteed by the operating system. So anywhere where there's these brackets around the operation here, that those will always happen what we call atomically, or those will never have a race condition, okay? This is stuff baked into the hardware to ensure that this mutex itself for the lock and the unlock operations can't happen concurrently. Okay, so that's the operating system's responsibility. Okay, so again, here's our examples and how to use a general purpose semaphore, which we'll just be using mutexes in this class, but just so you know what the general purpose lock and unlock mechanisms are. Okay, so again, the basic idea is you associate a unique semaphore, call it mutex, initially with 1, with each shared variable that you have, such that there's one spot for a thread to enter, and then you surround that block of code with the corresponding mutex operations for lock and unlock. Okay, binary semaphores are just the same as mutexes, always a value of 0 or 1. And then you can have a counting semaphore, which is the more general purpose if you want to allow, say, 5 threads to execute at once. Okay, so the pros and cons of these sort of thread-based designs are, it's an easier data structure to work with, between different threads, and they're more efficient than processes, right? They're lightweight threads. That's what we sort of discussed. Now the cons of working with threads are, we have these issues of unintentionally sharing data. Can be hard to sort of debug some of these issues, so we have to be just a little bit careful with how we do it. So that's sort of the greatest strength and the weakness of sharing this data, right? And trying to figure out what information is public and private and can actually be shared between things. And it can be, again, hard to find errors by testing because, as you saw when we ran our counting program here, it's hard to know exactly what's causing that counter to be a different value every time, okay? You can imagine a different or a bigger program, okay? Okay, so the summary here is that programmers just need a clear model of how variables are shared by threads, and we sort of have that here, okay? Variables that are shared between multiple threads, well, we need some mechanism to protect them, right? That's why we have the mutex. And the semaphore is the most fundamental primitive to do that, okay? And we saw the example of binary semaphore, which is just a mutex. Okay, so go ahead and give yourself a little break if you need it, and then we'll move on to the next topic. All right, and the next topic is Continuing with concurrency, here's just another review of it. Again, another view of the binary semaphore or a mutex. Again, just a special purpose instance of a semaphore. They just call it a mutex, and it protects a shared variable. Okay. And here was our API. I want to go through this quickly, so it's not as important, but conceptually it's useful for you to know, just using locks to write thread safe code, what's going on. Again, the terms. The area you're surrounding the lock with is what's known as a critical section. Okay, that's the code protected between a lock or a semaphore. And there's different sort of levels of what we call thread safety. And we want all of our functions that we call in C programs to be sort of thread safe, meaning you don't have to worry about putting locks around them, okay, as a user. If you're just using a function like malloc, you don't want to have to worry about if it's thread safe. You just want to know that it is, okay? And you have to follow certain rules to make that happen, okay? Because if you don't have thread safety, right, you get data races and deadlock. If you want to see a simple deadlock, let's actually just create one. That's what this slide is about here. I'll just make it a little bit bigger. But what I can do is for the first thread that executes, I can actually just get rid of the unlock. So that thread actually just holds on to the key the whole time, so to speak. And then it terminates down here and it never returns the key. It never releases this lock. So if I run this again, you'll see that the program just halts here, right? It just halts forever. Because the thread starts executing, it increments the counter, and then says, okay, I'm done, goodbye. And then all the other threads are still here waiting for the key, but the first thread ran away with it, right? As soon as it hit line 16, it terminated itself with the key. So that's an example of deadlock, where you forget to release a shared resource. Okay, so let's fix that, and now we're good. Okay. So again, the 4 safety classes, these aren't things that you have to memorize, but these are how you know your code is going to be thread safe. If you're writing a library of code that you'd want to share with someone, these are the rules that you have to follow. And the first is that you have functions that don't, if you have these functions that don't protect shared variables like we saw, that's sort of what we say a class 1 thread safety error. Okay. So the solution is just to, well, put locks around things. Okay, that's exactly what we did. The second thread safety issue is if you have functions that keep state across multiple invocations. So again, you have some perhaps static variable here, and it's just called next here. And then you have this function rand. So rand is a random number generator. It just returns a random number back. And it uses this variable next to sort of multiply by this value and just generate a new random number, okay? It does a pretty good job, but again, if I call rand in many threads all at the same time, it might share this next value, okay? And it's sort of a classic example. And you might say, well, Mike, we're just generating random numbers. Why do we care if they're the same or whatever? Well, actually in testing, it's actually very important that we can rely on some of these random numbers to come out in the same order, given some seed where I set next equal to a particular value, okay? So you might want repeatability where you're relying on the rand function in your program. It makes things more deterministic when you're testing, okay? And of course, always as best practice, you want your code to be thread safe. It's just the right thing to do, okay? So the fix is you can make this, instead of having that global or that static variable, next is instead you pass in as a parameter what that value is going to be. So every time this function's called, it's getting passed in the next p value, okay? This makes it what we call a reentrant function. So sometimes you'll see these in the C library where they have an _r. And then you can get rid of that static variable, okay? You just call it with this value. Okay, so your input is keeping track of this state. You sort of move your problem elsewhere. Okay, so reentrant functions are thread safe functions, okay? And they're sort of nice because they don't require any synchronization. You didn't have to do any locking or unlocking of anything. But you're sort of just relying on the user to pass in a new variable here, okay? The third class is functions that return a pointer to a static variable. So you can have a function like this. Remember, static is something that's shared within all invocations of this function. Okay, so every time you call itoa or integer to string, this function here has a static variable that would be shared. So you're returning something that could potentially be shared amongst two threads that are executing this. Okay. So the solution for this one is to use locks and try to rewrite the function to return the address of the variable. Okay, so this returns the pointer for this value here, but we do a little bit of refactoring here to, again, put a lock around our value here, and this makes things thread safe. Okay, and then we're not returning something that's static or shared amongst different instances. In fact, we're passing in a copy of something here. Okay. Then the fourth thread safety class to make our functions thread safe is, well, this one's kind of a nice one. Functions that call thread unsafe functions are also themselves thread unsafe. Okay. And that sort of, then the solution to that is just don't call thread unsafe functions within yours. Make sure that they follow these other rules here. Okay. How will you know, which functions are thread safe? Let me actually just show you here. So if you go on the manual page and, let's pick one like scanf, usually it'll tell you somewhere in the help guide if it is a thread safe function here. So if I scroll down to the bottom, sometimes it'll say in the notes section, sometimes it'll have the attributes, and this one happens too. So for thread safety, it says it is multi-threaded safe. So the scanf function where you're reading input, for example, is fine to use. They've already put locks in that function for you. Okay. So do you think, these functions I've shown you, scanf is thread safe? What about malloc, free, and printf? I'll give folks a moment to pause and think about that. If you've taken a moment to pause and think about that, well, yes, these functions definitely have to be thread safe. Again, remember, if you have two threads that are allocating memory, you want to ensure that they're giving you new pieces of memory, not the same piece of memory. That would cause quite a bit of problems. Okay. Most the C library functions that you're going to be using are thread safe. If they're for some reason not thread safe, there's usually a reentrant version of that function. Again, that's what the _r means in case you happen to see those. And that way you can use these functions to have something that's thread safe. Again, if you have a multi-threaded program. Okay, and I just want to leave you with one semaphore example. So here it is. In this example, I'm actually going to write it up for you as well. Let me close this down and write semaphore. And so you can see what's different here. Again, we need our standard library. We're going to need standard lib, the Unix standard here, library, and then the new library. So instead of pthreads this time is I'm going to include semaphore. Okay, semaphore.h. Okay, let's define. I'll follow this example, 9 threads here, and then we're going to create our semaphore. I'm going to call it barrier. Okay, so let's start sketching this out here. I'm going to have a main program with the return 0, the main function. Let's create our pthreads and store the ID. The pthread library is stored inside of semaphore, so it's already included there. That's why I didn't include it this time. And we're going to have a number of threads here. Okay, and just use this value. Okay, for the semaphore, we similarly need to initialize it, and we use the seminit function. 0 is going to be sort of the initial value, and I'm going to follow the example and put 3, and the 3 means this time it's not a binary semaphore or a mutex, but we're going to allow 3 threads to execute a piece of code at once. Okay, it's kind of like a bouncer at a restaurant that lets 3 people in at a time. And then every time, if one person leaves, then another person can come in. If 5 people leave, then as many as 3 can come in. Okay, that's the idea. That's letting 3 things in at a time, and then 1, 2, or 3 people can leave at once. And then as soon as somebody leaves, somebody else can come in. Okay, so let's create our threads again, just so you can see the practice here. Number of threads. And again, we always create, when we're trying to do something in parallel, we're always creating all of the threads at once here. So I'm going to store their IDs in this array. No special arguments. We'll have a thread function and no arguments in that function. And then I'm going to join all my threads after. Okay, so I'll have a similar loop here. I is left the number of threads plus I, and then join these together. Okay. Because if I actually, if I put this right after, so if I created a thread and then I joined it right away, this would essentially mean create the thread, wait, create the thread, wait, create the thread, and then wait. So then I would have essentially a sequential access. So that's why I have been instead creating the threads all in one loop, and then I join them all at once, okay, after they've all been created. So as soon as they're created, they can execute some code in parallel, okay? There we go. Okay, and then I need to destroy our semaphore once we're done with it. So that is the same as freeing it, except we're using their the appropriate C function to do that. And let's create a thread. Okay, so this is going to be our thread. It's not going to take in any arguments, but it can take in a variable number of arguments. Okay, and for our semaphore, this is the barrier pattern. So you have a barrier that allows in 3 things at once. And I'm just going to print off a message, hello from a thread, as shown, and then just sleep that thread for 1 second, just so you can see. Or let's actually do 2 seconds. And then I will release that semaphore, okay, or that thread that's executing here. And then our post is the equivalent of unlock in the semaphore terminology. So you'll see those a little bit different terminologies. That's why I like the mutex, because it's just lock and unlock, where this is wait and post. So you can think of wait as wait, and if there's a spot, let me in immediately. And post is sort of a, think of it as a sort of an increment operation, post, or +1 or something to your semaphore. One more person's allowed to enter as soon as the thread executes this. Okay. Then our thread needs to return something, so it's just going to return null. And let's go ahead and execute this. And I'm just going to compile this with GCC. This is the semaphore.c-o semaphore. We name our program, and we still need to link in the thread library here. Okay. Looks like I made a few mistakes here, so let's go ahead and fix those. I just need to call this thread IDs. And I fix one thing at a time. And it looks like it doesn't like pthread create. It says the implicit declaration. Okay, so let me just include pthread. So I was able to figure it out, but let's just include the library. I'll update that in the code, and it's happy now. Okay, so let's run semaphore. And you can see 3 threads execute at a time. They each take 2 seconds to process, and then, other threads start executing in this block of code here. So it's pretty neat way to model your programs, where you can do 3 things at once, okay, or as many as 3. And of course, we can play around with these numbers, and you can increment this to 9 or 10 or whatever, and you can play around with the barrier, okay, in these examples. Okay, so there's other common concurrency patterns. That was called the barrier pattern. There's a signaling pattern. There's a dancer pattern, producer-consumer, reader-writers. These are all sort of common patterns for writing concurrent programs. Just something to be aware of, and you might need to use a semaphore to implement some of these. So I wanted to show that more advanced construct, okay? For folks who do want to become an expert at this, or maybe you're super excited about this, in the full systems class, you'll learn more. But there's an excellent free book from Professor Alan Downey on this topic called The Little Book of Semaphores. These examples are actually all in Python, which is nice as well. And then there is the Programming with POSIX threadbook, which is pretty good. Okay, so with that said, folks, that's it on concurrency. We have what I think is one of the more fun assignments to do because you'll get a little bit of visual output of what the threads are doing. And then we will go from there. So look forward to talking to folks in class, and we will keep making some progress.